So Aditya mission, you can think of this that it is going to complement many missions which have been launched by various space agencies in the past. And I do feel that space allows this collaboration among nations, and that is great for humanity. So Aditya L1 mission has been placed around L1, which is 1.5 million kilometer away from Earth towards Sun. Parker probe is one of the most ambitious missions launched by human beings. So as of now, Parker probe is literally traveling inside solar corona. So the best theory that why the temperature is less compared to the surrounding is that intense magnetic activity is going inside these regions, and that magnetic activity is not allowing the energy which is being produced in the inner layer of sun to come on the surface, and because of that the temperature is less compared to the surrounding. Understanding about all of these words I mentioned earlier, as well as geomagnetic storm, what exactly it is, as well as what are the impact of geomagnetic storm, as well as what are the scientific objectives of Aditya L1 mission, what is Lagrange point, why Lagrange point, right? So all of these questions you can expect in prelims or mains examination.
Hello and welcome to the conversational video series brought to you by VisionIAS. In today's session, we're going to know about one of the India's remarkable achievements in the field of astronomy, which is Aditya L1 Mission, a solar mission launched by the ISRO. To enlighten us about the same, today we have with us an eminent VisionIAS faculty member, Abhishek Sir. Hello, sir.
Thank you, Chiranjeev.
So let's begin this discussion with a very basic question. What exactly is Aditya L1 Mission?
Aditya L1 mission is first dedicated solar observatory launched by ISRO. ISRO, whatever information we have gathered about sun, particularly done by ISRO, it was with help of some scientific instruments located on the ground, but a dedicated observatory placed 1.5 million kilometer away from Earth around a point known as Lagrange point 1. This was achieved by ISRO recently, and that has potential to enlighten us more about sun and its layers and a lot of events associated with sun.
Now, one more question, which may be very basic in nature again, but just for our general viewers. Why is it important to study the sun further?
That's actually a very good question. We know that without sun there is no life. However, we still do not know a lot about sun. We know, for example, sun has multiple layers. At the core, nuclear fusion happens. And that nuclear fusion, which happens at about 15-20 million degrees Celsius, powers the entire star. But when you go to many layers, convective zone, radiative zone, and when you finally come to the surface of the sun, the part of the layer of the sun which we can see with our naked eyes, that is called photosphere, and the temperature reduces to about 5500 degrees Celsius. But then you have two more layers which is not visible to our eyes, but they are there. With help of telescopes we can gather more information about them. They are called chromosphere and corona. So to understand about these layers itself, then on photosphere you witness something very interesting which is called sunspots. And sunspot activity is very much associated with few events known as solar flare and coronal mass ejection. And all of these things do have some impact on Earth also. And frankly, we do not understand about all of those things really well. We do know that they happen. We also have some theories that why do they happen, but we want to confirm those theories further by gathering more information. And that is what Aditya L1 mission aims to do.
So, mentioned a few keywords, CME, coronal mass ejection. We'll come to that later. But before that, we'd like to know, as Aditya L1 Mission is a space observatory, what are its structural and functional aspects?
Okay, so that's again another very good question. So Aditya L1 mission is, you can think of this as a one observatory, but this one observatory had 7 scientific instruments, and all of those 7 scientific instruments have different responsibilities. So for example, one of the instrument is capturing images of the layers of sun such as photosphere and chromosphere in not just visible light but also in ultraviolet light. And then you also have another scientific payload which is trying to understand about solar winds. You have a payload which is trying to understand about X-ray flares. You have payload, which is trying to, one of the scientific instrument which is trying to understand about the nature of interplanetary magnetic field. So as solar particles emanate from sun and reaches to the entire solar system, so what is the nature of the interplanetary magnetic field? All of that we aim to know with help of the 7 scientific instruments.
Now, could you, sir, please distinguish between solar winds, solar storm, coronal mass ejections, etc.? They're very confusing.
Yeah, they are. So, and all of them actually they do mean different things. So let's start with solar flare, for example. Solar flare, you can think of this as a massive burst of electromagnetic radiation, which mostly lies in UV and X-ray, but it can also lie in visible light and infrared also. And solar flare is a very bright event. Uh, in fact, many people often compare the amount of energy which is produced in one very powerful solar flare. You can think of thousands of atomic bombs exploding together. So it's a very bright event. But it essentially is electromagnetic radiation which travels with speed of light. So solar flare is immediately visible to us. It may not be visible to us with naked eyes given the fact that sun is really huge and solar flare emanates from a specific region on sun. But with help of powerful telescopes, with help of observatories, we get to know about that. So that is the first thing, right? Second thing which you said, coronal mass ejection. Coronal mass ejection is now not a burst of radiation, electromagnetic radiation, but it is burst of plasma and magnetic field of sun. And you can think of billions of kg of highly charged magnetized particles, which mostly are protons, electrons, or even alpha particles, which essentially is helium, being emanating in a very specific direction. So they do travel with very high speed, but not with speed of light. And it is going to take about few hours. It can take about 12 hours, 15 hours, or even 20, 30 hours before it can reach to Earth. So coronal mass ejection is a stream of charged particles, while solar flare is burst of electromagnetic radiation. The third word you mentioned is solar wind. So solar wind is also a stream of charged particles. However, it is not as intense as coronal mass ejection. Solar wind particularly emanates from a region called coronal hole on sun, and I often think of solar wind versus coronal mass ejection. You can think of this as a wind and a storm. So coronal mass ejection is a very, very powerful ejection of charged magnetized particle. Solar wind is a very mild version of that. And solar wind is a more frequent phenomena, while coronal mass ejection is much more rarer compared to solar wind. And solar storm is a word which essentially includes all of these three words, like one common word where we are using all of these events, and of course we are also describing the impact of these events on Earth, and all of that together we can call this solar storm. So yes, all of these words often used interchangeably, but they do have different meaning.
Thank you, sir, for clarifying doubts. Now, the next question is L1, that is Lagrange 1. What exactly are Lagrange points?
Okay, so Aditya L1 mission has been placed around L1, which is 1.5 million kilometer away from Earth towards Sun. And it's very interesting. For example, we know some basic about orbital mechanics, that when an object attains a stable orbit, it needs centripetal force, right? And for that centripetal force, we essentially utilize gravitational attraction. So for example, think of a satellite revolving around Earth. That satellite can revolve because the attraction of Earth, which is gravitational force, is providing the necessary centripetal force. And when we are talking about orbit of a satellite, we do not have to bother about impact of moon or sun. It's not that they do not have any impact, but whatever that impact is, it is negligible. But if you keep going farther away from Earth, then other objects and their impact cannot be neglected. So Lagrange, who was a great mathematician and a great physicist, he thought that can we find a stable orbit not because of one heavy object, but because of two heavy objects. So you can think of, and the answer is that he did find that, and this was simply a mathematical curiosity. He simply wanted to solve a maths that can a very small object find a stable orbit, but that stability is because of two heavier objects. And he came to a conclusion that there are 5 such points for two heavier objects, where a third very smaller object can be placed, and this third very smaller object does find a stable orbit, but this stability is not because of either one or two, it is the combined effect of both of them. So now let's use this into practice. Think of first heavy object as Sun, second heavy object as Earth, and think of Aditya mission as my third smaller object. And it goes without saying that Aditya L1 mission mass will be negligible compared to mass of Earth and Sun. So the assumptions made by Lagrange fit perfectly here, right? So now L1 is a point where you have a mission which can continuously observe Sun, right? But as Earth is revolving around Sun, L1 is also revolving around Sun. So in a way, even Aditya L1 mission is continuously revolving around Sun, but it is not going far away from Earth. Now this is actually quite interesting, because think about all the objects which are closer to Sun compared to Earth. They will revolve around Sun much more faster. Mercury revolves around Earth much more faster. Venus revolves around Earth slower than Mercury but faster than Earth. So if something is closer to Sun compared to Earth, it should revolve faster than Earth. We want to have a solar observatory which can continuously monitor Sun, right? Which L1 can do. But I also want to maintain some sort of synchronization, that whatever data is being gathered, the data can be received by antennas on Earth. So I do not want that my mission goes farther away from Earth and Earth is lagging behind. I want some sort of synchronization. And this is where Lagrange point 1 comes to place. That Aditya L1 mission has a, and by the way, Aditya L1 mission is not at L1 point. It is into a very complex 3D orbit which is called halo orbit. But even within, to be in this halo orbit, the necessary centripetal force comes from the combined effect of both Sun and Earth. So now I have this essential benefit that I can continuously monitor Sun without getting eclipsed by Earth or without getting eclipsed by Moon, and at the same time I can send information back to Earth and antennas on Earth can receive that information. And other Lagrange points also have a lot of applications. For example, L2 point has applications in launching telescopes. In a previous video, we talked about James Webb Space Telescope. So Webb telescope is around L2 point. L3 point is not very useful. L4 and L5 are also as of now not being used. Maybe they will have some application in future. And another interesting thing, I will conclude this answer with this last point, that it's not that Lagrange points are only there for Sun and Earth system. I can find Lagrange point for Sun and Jupiter system also. I can find Lagrange point for Earth and Moon system also. But it's just that Sun Earth system and the 5 Lagrange points are very useful for astronomers, and that is why there are many missions around Lagrange points.
That was perfectly well explained. So now coming to Aditya L1 mission, where does it stand as compared to other global missions?
Okay, so another global mission which has been in news a lot, I can mention about that, is Parker probe, Solar Parker probe, launched by NASA a few years ago. Parker probe is one of the most ambitious missions launched by human beings. So as of now, Parker probe is literally traveling inside solar corona with very, very high speed. And it aims to gather more information about coronal heating. By the way, I forgot to mention one thing. Just you asked a question earlier that what we do not know about Sun. One of the most mysterious event about Sun is that solar corona, which you can think of as the atmosphere of Sun or the outermost layer of Sun. Solar corona temperature is few million degrees Celsius. So as I said, the core temperature is 15 to 20 million degrees Celsius. Photosphere is 5500 degrees Celsius. Then corona, however, solar corona temperature increases to 1 or even 2 or sometimes 3 million degrees Celsius. This is called coronal heating. But again, we do not understand really well that why coronal heating happens or why corona is at such high temperature. So Parker probe, for example, aims to gather more information about this mysterious layer of Sun which we call corona. There have been other missions. There is a mission by European Space Agency which particularly is interested in knowing about the poles of Sun. There have been some past, there is a mission of NASA called SOHO mission, Solar and Heliospheric Observatory, which also has some general objective regarding gathering information about various events associated with sun and various layers. So Aditya mission, you can think of this that it is going to complement many missions which have been launched by various space agencies in the past. And I do feel that space allows this collaboration among nations, and that is great for humanity.
True, sir. I was supposed to ask another question related to sunspots. What exactly are sunspots? We often come across this term in geography as well as in space science.
Okay, now this is another very good question. Sunspots are regions on the photosphere where temperature is less compared to the surrounding. And because of that, when you do thermal imaging of sun, in that thermal imaging, they appear darker, right? So the best theory that why the temperature is less compared to the surrounding is that intense magnetic activity is going inside these regions, and that magnetic activity is not allowing the energy which is being produced in the inner layer of sun to come on the surface, and because of that the temperature is less compared to the surrounding. You can think of this as a rubber which has been squeezed very tightly, right? So there is intense magnetic activity going here inside sunspot, but sometimes when magnetic fields realign, that suddenly expels lot of radiation, which is essentially what we call solar flare, as I mentioned earlier. And an associated event can occur which occurs from corona, that billions of tons of plasma lifting out of corona and getting released into entire solar system, right? So sunspots are closely associated with solar flares as well as coronal mass ejection. Sunspots are not permanent spots on photosphere. In fact, sunspots, they appear randomly on the surface of sun, they grow in area and then they again shrink. And many sunspots can emerge on different part of sun. But there is a very interesting thing we find here, that it happens in a cyclical manner. So for example, let's say the total area occupied by sunspot on photosphere, it goes to a minimum, then it reaches to a maximum, and then again it comes to a minimum. So now we have a cycle. The cycle is called solar minimum, maximum, solar minimum. So between either solar minimum or another solar minimum, or solar maximum or another solar maximum, about 11 years passes through, right? So scientists often use this to assign probability of solar flare event or coronal mass ejection event, that whenever solar flare is maximum, at its maximum, then the probability of flares and coronal mass ejections is very high. Right. So this is exactly what sunspots are. But we want to gather more information about them. We want to understand exact mechanism, how do they happen, and hopefully we'll be able to predict also that where they will emerge in future.
The last important concept that we wanted to know from you. Now coming to the importance or the relevance of Aditya L1 mission with regard to the Indian space science sector and in general.
To answer that, I should also tell you that, as I mentioned earlier, that solar flares or coronal mass ejections or solar wind, they do affect Earth, right? So Earth has a very powerful magnetic field, but because of for example, let's say coronal mass ejection, Earth's magnetic field undergoes fundamental certain changes, and those changes essentially lead to a lot of events. For example, we witness aurora. In polar regions, we witness aurora quite often, but we can witness aurora in lower latitudes also when there is a very powerful solar storm. A collective term for such type of changes in Earth's magnetic field is called geomagnetic storm, right? So geomagnetic storm can lead to aurora, but if it is very strong, it is very powerful, it can also disrupt our communication satellites, our navigational satellites, and if it is even more powerful, it can also disrupt our power transmission lines and it can cause blackout. So why Aditya L1 mission is significant? Because India wants to enhance its capability in making such type of predictions and we are trying to understand more about how solar storm can affect Earth in various ways, right? So definitely our satellite program and space program will benefit from Aditya L1 mission. I also feel that this topic is important for UPSC because we are also talking about UPSC aspirants here. So you can think of understanding about all of these words I mentioned earlier, as well as geomagnetic storm, what exactly it is, as well as what are the impact of geomagnetic storm, as well as what are the scientific objectives of Aditya L1 mission, what is Lagrange point, why Lagrange point, right? So all of these questions you can expect in prelims or mains examination.
I think we have very comprehensively covered this particular mission called Aditya L1 mission. Not just the mission, but also other solar phenomena. And so you also told us about the importance of this topic from the point of view of civil services exam. Thank you so much for your time and your valuable input, sir.
Thank you.
Now, dear viewers, we hope you enjoyed and liked the session. We'll keep coming up with more such sessions. Till then, stay safe and have a good day.